So this is what ChatGPT did actually. And then
Yeah. Second law, right?
and then I is and then because it's not slipping, its acceleration has to equal to the degree acceleration times r. And
If you are, let me think about it. The second equation, let me ask you. Second equation, when you do the torque like this, which is your rotation point? The torque is about which pivot?
the center.
Let's see. He's using this contact point as the. He's using this point. Which point are you using? You're using the center?
Yeah. I was just basing it off the center. It worked, but I'm just trying to rework it.
Yeah, if you use the center, there is a. If you use the center, which means you need friction, right?
Yeah.
You need friction. But you don't really have friction, right?
Yeah. I see what you're saying.
Which is which will cause a problem.
Maybe you could just explain how the textbook did it. That would also work.
Yeah. So your way
It's
also
kind of
works.
confusing.
Yeah, your way also works, but this way, a textbook is maybe easier because he's using. He want to use your method first, and then he find basically. Oh, you see, this frictional force is not part of the equation, which means you can't really find it directly. So that's why we do not use that center point as the rotation pivot. So we're using this one in the hope of this torque is zero. Does that make sense? Since I don't have friction, so I hope the torque of friction is zero. If I use this, because this friction goes through the pivot that I choose, right? P. Does that make sense?
Yeah.
Yeah. So since
it says it has friction though.
Yeah, it has friction, but it doesn't have torque. Does that make sense? It doesn't have
Why
torque.
is that? But if it had friction, wouldn't that just push that around?
Yeah, he pushed that around. He doesn't make a rotation about this point. Does that mean he make a rotation about this point? Does that mean
Oh,
so friction
because yeah,
make
that point's
yeah. He make this point a rotation. No, he make this rotation about this point. He make a rotation, but about this point P he choose. He does not make a rotation, which means he does not cause any real torque for this one, which is a good thing because when we find
What about this then?
Oh, that one is. So that one is the gravity's component. He's actually making a torque. So this is the gravity, right? If this is the gravity, he has a component who can make a torque about this point P. And he's the other component, which this one also goes through the pivot that we choose. This is actually very routine. You choose the pivot, try to make your equation easier. So we choose this P, or we can choose this one. So we choose this P, so in the hope of so this torque and also this torque is all zero. So the only torque I have to think about, the sigma torque, is mg sine theta torque. Does that make sense? Because all the other torque go through your pivot, so it doesn't really have torque anymore. Does that make sense?
Yeah, I get that part.
So you time let me erase that. You time the pivot to the action line of this force, which is this part, which means r perpendicular, which is r, right? So this is mg sine theta r. This is the force. And time, this is the sigma torque, right? Does that make sense? And it's the sigma torque about P. So we choose it, carefully. Actually, by tryout, we choose P. Otherwise, your choice is also a choice, choosing the zero, choosing the center. And so since this is the one that I can use what's this thing? And then I can use I alpha, right?
Yeah.
So here's the I and alpha. What's I then?
Alpha.
Alpha is the
I is. Wait, what is R? Is alpha the acceleration of the?
Oh, you mean
No,
I?
that's...
What's I is? What's the inertia?
Yeah, what's alpha again?
Alpha is the is what we find Newton's law is sigma F. So I get confused and I write that ma, right? In kind of an image of this coming from there, it's sigma torque, which is the reason why you rotate, as the last time your reason for changing acceleration. This is your I for m and a for angular acceleration. Does that make sense? So this is I alpha. So what's your I then this time?
Wait, so alpha is just I times alpha is the acceleration of the angle.
Yeah, acceleration is the alpha is the angular acceleration.
Oh, so it's this, right? It's okay.
Yeah, and so what's the I for this time?
1/2 mass times radius.
We just find the
Squared.
cylinders one from the previous question. Remember that?
No, I don't remember.
Let's see.
What question number is it?
Let's see which one. This. Oh, this one. Remember this is a cylinder, it rotate. We use R, integrate R squared dm. And then we find eventually, what we find is actually this one. But when we change the form, it eventually comes into this, which is 1/2 mr squared.
That's only for cylinders though, right?
Yeah.
Do we have to derive this every time, or is it better to memorize this?
Yeah, it's better. Would definitely memorize that. And because cylinder is also very typical. For example, pulley is a certain kind of cylinder, right? Or CD, or well, just cylinder itself. Yes. So we use that a lot. So it's better to.
So basically, the only other thing you had to do is like a sphere, but that's it.
Yeah, kind of.
Maybe something like else, but right now, yeah.
So what's now we have the cylinder one, which is 1/2 mr squared, right? That explain that. Does it make sense? The I?
Yeah.
And alpha, we also have something. Let me get the question. This is the cylinder, and here's the center. Oh, and also we draw something from a previous question. We also have to kind of use that. So this one is 1/2 mr squared. But we also have a excess, like a theorem. Let me get the excess theorem. Do you remember this question? In here, we have parallel axis theorem.
Yes, I actually did write that down somewhere.
Well, too bad we didn't do it in one class. So it's we have to remember, we have to use this one too. So because 1/2 mr squared is use it for the center is actually the center of the cylinder. Does that make sense? This is the inertia there. But
So we can't use it for this one?
Yeah, we can't use it, but that will only be this one. Does that make sense? Remember? Only the first term is that. So what we actually use is because we choose this one, we basically choose a new one, right? We basically choose a parallel axis. Before the axis, you know, it's kind of like in here. Now the axis is parallel in here. Does that make sense? You rotate. When we write 1/2 mr squared, we assume the center, you just basically rotate about this one. Does that mean you rotate around this center? But now, since we're choosing the pivot as this one, so we're using the parallel axis theorem. Does that make sense?
Oh, wait, no, I actually didn't do that because I was doing it around the center. Okay, let me write that down.
Yeah, so that's why
I got that mixed up with transitional law, the MG sine one.
Oh. So do you remember parallel axis?
Vividly.
Okay,
not vividly, a bit, yeah.
Okay.
Mixing up my book.
Let me write this. Then let me draw this. See this one. See this
Wait,
question. This is the question that we try to use the parallel axis theorem. It's because this is the center of that, which is we basically find which is this one, 1/2 ml squared. If you rotate about this one, and then we find that if you rotate about this point, it's becoming 5/4 ml squared. Do you remember that?
Yeah. This might be a dumb question.
Yeah.
But could you give me all the units? Like, for example, what is I versus ICM? And then is X like the distance from the center or?
Distance from the center, from your original system of the center to your new axis, you rotate. This is X basically.
Okay, so from the point we're looking at to the next point, right?
Yes.
No, from the starting point to the point.
Yeah, from the original center to the new axis or new pivot that you rotate. Does that make sense? So that's the I equals to I, center of the mass, plus your M, X squared.
Wait, why is the pivot changing again?
Well, you can say it's the same rotation, but it's for this one, for our case, it's actually the same. But for this one, it's actually different. You see, before you rotate about this, right? It's basically you're going like this. You rotate about this, right? This is the first A question, right? And then for the second one, you actually rotate around this, which means you're doing this. Does that make sense? That's different. Does that make sense? Am I making sense? Before you rotate around this for A, but for B you rotate around this. This is how you rotate. So this is your axis. This is your axis. Does that make sense? So it's a different rotation, basically, right? Around different center, around different axis, or around different pivot. Does that make sense?
Yeah, because you're getting a different radius. Yeah, I see.
Yeah. But they are actually the same. There are something connected. They are the same system, right? It's all the three object system, right? Connected by this line, or actually points by this whatever this is. And so it's a system. It's the same system. So that's why we use I, center of the system, and plus your new thing, mx theta squared, and equals to my new inertia when you do this rotation. And for this one, if I can use, I can use this one also using this one, because this one is just the x is 0, so that's why it's using that. Does that make sense?
Yeah.
If you
I
remember
have
this,
another question.
Sure.
Yeah, sorry, but
Okay.
I don't know if you answered this already, but what's the difference between I and ICM? Like
Oh,
this.
ICM is basically A. You rotate
So
around
okay.
your center of the system. You rotate, see, this is the center of the system, right? This is the center of the system. You rotate around that, about that. Does that make sense? You rotate, this is the rotation you do, right? Can you imagine this?
Yeah, so it's basically the radius.
Yeah, around that, this radius. And for the eye, you're not rotate about the center anymore. You rotate about this, like let's say this point A. You rotate about point A. It's different. Does that make sense?
Oh, so this is like the initial radius and this is the final.
Kind of like that. Yeah. That's a good reference. Yes, it's kind of like that. This is the original initial.
What's the
like,
difference?
It's a different rotation. So that's why you use a formula to find the final rotation or the new rotation inertia. It's a different rotation, so that's why it's different inertia. Does that make sense? Let me get my camera.
Oh no, like what's the difference between radius and like the initial radius, final radius, and these?
It's not
Like the I.
you mean the readers? Or readers before is L over 2. Now readers is becoming L. But I don't think readers is readers is different, but it's kind of not the key, the readers. Readers is a part of the problem though. You're finding they have new readers, right?
Yeah.
The most key here is they have the new center, or they have the new rotation pivot axis. Does that make sense?
Yeah.
You understand
I
the
still
two
don't
different.
exactly get what I is though.
I is the new I center of the mass, basically. Because before you rotate around this, and we find out with the formula we can find out ICM. ICM is okay, right?
Yeah, that's
But
this
now,
right here.
now, when you rotate, for example, when you rotate, forget about that I. Let's take a look at question B. Question B asks you, basically, what's the question B? Figure out the rotation inertia for B. So how do you find? That's answer your question. How do you answer B? Inertia.
I know it's something with this, so you would put. Let me give me this pencil. Okay. So, and then.
Wait, since you don't really get this question, you can use the original definition. The original definition, they can just find your I anyway. Find your I. Do not, since we do not, you get question about do not use this. You can just use the normal way we do it, which is sigma mi ri squared, right? Is this okay? This is the initial definition, right?
Yeah, so all the. Okay. Yeah.
You can just add all of them. This one, I remember you did it yourself. Okay. M, if I talk about this point, 1, 2, 3. 1 is M0 square, right? M times 0 square. Plus my M2 is also M, L over 2 square. Plus my M3 is M times L square, right? Does that make sense? So basically, this is I.
Yeah.
So you ask me what is I? This is I, right? Don't use that theorem yet. So this is I anyway, right? By definition.
Yeah, and then ICM for which one's the initial one? Is it A?
Yeah, A is the initial one. Center of the system.
So this would be okay.
Center of the mass of the system.
So this A would be ICM. So
yes.
ICM is equal to, let's see, M times 0 squared plus M times 2M times L/2.
Yeah, exactly.
Okay, so the difference is just that, and then.
Oh, the data difference is that, and also it's a different phenomenon, right? One is rotate like that, the other one is rotate like that. The different rotation, right?
Yeah, I get what you're saying now. And then to complete it, all you have to do is move it all to one side, right?
Yeah. And then they said, now we say they are different, right? Now we say that different. But they also have a connection, which is our parallel axis theorem comes in. I equals to I center of the mass plus mx squared.
Mm.
Does that
Okay,
make
yes, that actually does make sense because
sense?
like this one is bigger,
Yeah.
right? So
Yeah. This
you
is
had to
kind of
add
like
something.
original something, rotate about that. And oh, you are right about that. We actually didn't prove that. Oh. The 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 textbook doesn't require us to prove it anymore. We accumulate data that we can use that. So basically, they find this kind of thing always have a connection, and that connection is that mx squared. The difference is that it's kind of like because you move your center from here and to here, so that's why there's a change mx squared. Does that make sense? Which is making a little sense,
Yeah.
right? Because you're changing the center, original thing stays, but you're changing something, you gotta kind of make up. So now I can use
Yeah.
it for our question 14, which is the I.
Wait, that suggests that it always gets bigger, the
Yeah,
inertia.
basically, always a bit bigger.
Oh yeah, as you move to the sides. Yeah, I get
Yeah.
it. Mhm.
You need a little bit, it's a little bit harder. I mean, see, when you rotate like this, it's a little difficult. It's okay. When you rotate like this, it's a little bit more difficult, right?
Yeah, to stop it.
Yeah. I mean, to start, not just to stop. Oh, to stop it is actually the same. You all try to make a change. To start it is to make a change. To stop it is also to make a change. So now we're using this, and also the cylinder is like a 1/2 thing. Now we're using this for this one. Now we have. Let me write down. I alpha is becoming 1/2 mr squared, which is the cylinder thing, right? Which is the basically center of the math. I mean, plus because I'm rotate about this point, so I move the axis. So I need to add my mr, which you're moving from the center to this. This is x, right? The plus mx
Yeah.
squared, which is mr squared. Does that make sense? If I write this is my new inertia around my point, let's say this point is P. Oh, he's using P. Does that make sense?
Yeah. Okay.
And then time my alpha. Since the key here is find what? The key here is find the. What does he want? Linear acceleration. So I'm using linear acceleration more. So it's A over R, right? Because A equals to R alpha. Do you remember this?
Yeah. At least now.
So I can use this. Well, we can prove this. This is required and not difficult to prove. And so if that's the case, and this side is mg sine theta, which is this doing the torque, doing the total torque for the actual working torque, and time the r. So that's one thing that I can do. Does that make sense? So I can find A with this one. I can find A for this one, right? If I answer the first question, acceleration of the cylinder. Does that make sense?
Yes.
Does that make sense? Just find it.
And then
Simplify everything. Simplify everything. So we basically, the big equation is that sigma torque equals to I alpha. Now I just find, oh, what's I, what's alpha related to acceleration. and what's the actual torque and which axis that I should use. Two choice. One is using this. One is using this one. It's easier. Using this one is our choice here. Does that make sense?
Yeah, it's better. And then I'll do it again. Just to like. Yeah,
Rotation.
because you
Rotation.
kinda lost me here.
Which part? Which part?
Yeah.
Oh, the original. This one is okay, right? Because we use a little time to find the theorem that I have to use
Yeah,
to
I
find
get
R.
that.
And then we use this one, basically. Sigma torque
Change it in.
yeah, is causing my angular acceleration, sigma torque. And sigma torque, because the P that we do, all the forces, which basically is the gravity and the friction and the normal force. And this torque is zero, this torque is zero, and this component torque, so the only torque is an mg sine theta torque. Does that make sense? Mg sine theta is only one doing the actual torque here, times R. Does that make sense? This is sigma torque.
Yeah, and okay, so change in the friction equals to the inertia, which
Well,
is
not friction. Friction is zero, so that I didn't write it. Actually, it's a 3 0 0 0 0 because normal goes through the pivot that I choose, and the friction goes through the pivot I choose. So that their torque is zero because their R perpendicular is zero. Does that mean?
Oh yeah. So that basically means that, and then we know that alpha isn't zero because it like the circle is turning around. So
yeah. From the rest, it turns around. Yes, not because it turns around. It's because from rest it turns around. If it turns around, it can also means alpha doesn't change. But yeah, alpha changes. Is the angular acceleration.
So basically, all of the mass times distance.
Mass times this. You mean mx squared? Are you talking about that? Oh, you're using this one. Oh, this one. Yeah, this can also find the same result as this one.
So basically, this equals zero for this point.
Which is zero? Not all of them. Only mg sine theta can have an actual like torque. All the other forces have zero torque around P.
Yeah, that's why it's zero, because this is zero, right?
Wait,
no.
This is because mg sine theta times r. All the other, this force gets zero torque. This normal force gets zero torque, and friction gets zero torque. Also, component of the mg sine theta that goes through this in perpendicular to the slope. Yeah, this one also zero torque. They all go through the point P that we choose on purpose. We choose P on purpose, so all their torque can be zero, which is easier for us. Does that make sense?
Yeah. Okay. And then, so this is correct, right? And I fixed it.
Yes, that one. Yeah.
And then from there,
R, mg sine theta r. Another time. Oh wait, that's only the I, right? Wait, what's that? Oh, if you are you finding the the I? Are you finding the I for this one? This one is I actually.
Yeah, I was wondering how that would lead us to get the acceleration.
Oh, this formula is actually finding the inertia.
Yeah, how do we get the acceleration then?
Acceleration is using A equals to R times alpha.
Oh, so we had to find alpha instead. Okay, so we're
using
A
move
this over.
Yeah, A to express alpha. So I can just substitute this one in here. Or substitute this one in here, actually. Oh, in here, alpha. This part.
Yeah, but if we do that, we get the wrong answer, right?
Wait.
Because A equals R times alpha.
Yeah. So alpha equals to A over R. Alpha equals to A over R. Does that make sense?
That comes. Where does A over R come from?
Oh, it comes from here. You know.
Oh,
make-
okay, yeah, just that.
Does that make sense? This one? I can prove this, and this one also required. Also, it's easy to prove.
Okay, no, I got that, but and then
Thought
from
of you
there
were
you just. Okay, it's actually easier than I thought.
Rotation is
If
good.
it's just like that.
So now I have A over R instead of alpha, angular acceleration. So now I have the torque, sigma torque, which is this one. And all I need is the I, the inertia around P, right? Which I use parallel axis theorem. Sorry, this is all combined with previous knowledge. So this is using that. I find my new inertia around P. Not new inertia, it's the inertia that I choose. So this is I center, right? Of the cylinder. And this is mx squared, mr squared. It's because you're using this one. This is x, basically.
Yeah.
And
then yeah, it's actually easier than I thought because all I do is get this, right?
Yeah.
Yeah, the board's kind of cluttered right now.
Yeah, so
It's fine.
this is x, right? This is x.
Mm-hmm.
So this is the original center, which if you only rotate it by yourself, this is your center, right? But now you rotate around P, right? Now you rotate around P. So this is X is R, basically, right? X is R. So I can find my inertia for this system about point P. Does that make sense?
Okay, yeah, I'm starting to get it. Because once you have this, right, that is.
Yeah, this is for alpha. I want to use this one for instead of alpha. Otherwise, I find it's alpha, but I want acceleration. You can also, before I actually find alpha first, and then you can just use alpha times your R, then you can get the acceleration.
Oh, yeah, so you can get the acceleration.
Yeah. That one may be easier. Find alpha.
Alpha is equals to
all this divided by all this, I guess.
Oh, yeah, from the I equation.
Yeah. Basically, alpha is sigma torque over I. Right?
Okay, wait. Alpha. Okay, I need to start writing it like that because I try to write like this and it gets mixed up. Okay, anyways.
Yeah.
Let me erase this. Alpha equals what is it again?
Sigma torque over I. Yes, that one. Because it comes from this, right?
And then sigma torque comes from
mg sine theta
it's just
r. Yeah. Because I analyze all the other forces. Sorry, they don't have torque about my P.
Okay. Okay, I see how it is mg sine theta, but how do we find a change in that? It's you don't really get anything, right? I guess it could just be. Does it like accelerate? Like this, get bigger?
Yeah, and this is divided
by.
by.
We just do that.
Sigma. You mean delta?
Change in that. Yeah, like changing
Wait,
that.
wait. M doesn't change. Theta doesn't change. So it's a constant number.
Oh, so it's just 0?
No, no, no. It's a constant number. I mean, I'm saying M is
Oh, yeah,
certain,
all of them
theta
add
is certain,
together.
right? See, you have a certain mass, you have a certain theta. So mg sine theta is just a constant number, kind of.
And probably certain force of gravity too, yeah.
Yeah. G acceleration is certain. And then divided by I, which is this one, right? By axis, parallel axis theorem. 1 over 2 m r squared. This is my I center of the mass. And plus my mx squared, which is mass times r squared. So that'll be my alpha then, right? Yes.
Yeah. It'd be good if you could send an like a worked out, like one of these, just send it to me so I could do
Sure.
it.
Let me just erase
Yeah, but
everything.
I think, yeah.
I think the only thing that's left right now is basically this. I think this one will just solve the question. This one. So we find alpha, which basically is
And then multiply that by r and you got the acceleration.
Yes, m is out. The g sine theta.
As well as one of these r's, right?
Oh yes, there's
Because
r
you're
here.
multiplying by r.
Yeah, there's r here. So g sine theta times r is out. One of r is out. So 1 over 2 r plus r, which is g sine theta over 3 over 2r, which is 2 over 3 g sine theta over r. Does that make sense? This is the one. And so, and then I can find acceleration by next step, which is acceleration equals to r alpha. So just use r time that 2g sine theta over 3r. Oh, r and r simplified. So 2g sine theta over 3. Yeah, that'd be the answer for acceleration.
Yeah.
Let me hear.
Yeah.
Yeah, rotation is difficult, and also it's not very, because rotation is not very obvious, right? I see things
And there's
change.
a lot of equation.
Yeah.
Also a lot of equations and symbols too that just mess it up.
Yeah, we like test teachers and new teachers sometimes about how to teach wave, also how to teach rotation sometimes. Because it's a messy for everyone, teacher or student. So me too. It's always messy. And also we don't observe a lot of rotation. That's also one thing. See, you drive the car, but who watches the rotation of the tire, right?
Yeah.
So anyway, the sad things, we rotate all the time by knowing it or but not knowing it. But it's not very obvious. So anyway, this is the question A, right? I mean, the first question that we answered. And they also asked us the coefficient.
And now that we know acceleration, it should be pretty easy, right? So
yeah, kind of. They can just use something that we do.
What's the formula again, though?
Yeah. So now we finished with the big one, which is sigma torque equals to I alpha, which is the second law for angular motion. Does that mean? We're using second law, right? Basically, the first question used the second law. It's just for angular motion, right? Does that make sense?
Yeah, I see it now.
So now let's also use second law, but this time is because you want friction, right? So what connect with friction? Not the torque that we choose, but the sigma f, that involves with friction, and equals to my ma, right? Does that make sense? This, so we're using second law, and now we use second law again for translation.
Oh yeah, because mass corresponds to inertia. I mean,
wait, this
inertia.
time they're talking about the. I don't want to use inertia this time because this time they talk about friction.
Yeah, I'm just saying it corresponds, right?
Yeah, like angular. Yes, and this angular is for torque. But we use the torque. We normally, this is also very typical. We normally use the torque, basically use the second law for angular for once, which is question 1, and second law for question 2. For translational. So angular and translational. So translational now is just sigma f. We still go back to the very fundamental diagram, which is the force is gravity and normal force, and the friction. I'm drawing the friction now because it's in here, not in here. It's because it's basically the same. So now we can say in this direction it balances with the normal force, right?
Yeah.
So this basically, let me see everything I know. mg cos theta is my normal force, is my gravity's component right in here. Does that make sense? mg cos theta.
Yes.
Yeah. So in the same spirit, so this is also mg cos theta, right? Because you balance in this direction, right? So that's why you don't move. You don't get away from the slope or get into the slope, right?
Yeah, because of normal force.
It balanced. So, and also in this direction, I assume this one is bigger, so I probably do this one. So this is the other component, which is mg sine theta. Remember, this one is mg sine theta.
Yeah.
If it is mg sine theta, how about, do I know friction? I know friction.
How's there friction?
They didn't give me directly, so that's why friction formula, do you remember? Mu Fn, right? Remember? Mu Fn.
Yeah. Isn't it static as well?
Yeah, this one is static is because, well, you roll, so it's basically kind of like static. So that's why it's without slipping, it's static. So it's mu Fn. So which means also the mu is in here in the question. Is probably, we're probably going in for the right direction. Mu time Fn is mg cos theta, right? We just said that. So I can just write mg cos theta. Does that make sense?
Yes.
So now I can say in this direction is all balanced, so they're out. So in this direction they are not balanced, so that's why you have acceleration. So I can just find in this mg sine theta, which is, I assume it is going in this direction. So I assume mg sine theta, which is higher, positive. M minus my mg, actually mu mg cos theta, which is my sigma f, right? This is my sigma f. Does that make sense?
Yes.
And so equals to mo, this m is all, that's I'm using what they give. So this is also mass time your acceleration, which you just find it, it's a, what, 2g sine theta over 3. 2g sine theta over 3, which is what we find, right? The first question. Yeah, I think in this question, the only thing you don't know is mu.
Yeah.
So mg is all out. So we can
how do we get that?
So we can simplify all mg. So what's left? It's sine theta minus mu cos theta equals to 2 sine theta over 3. See, this is a sine theta. There is a 2 over 3, so I can move it there and then move this in here. So now I have 1 over 3 sine theta equals to mu cos theta, right? Does that make sense? Because theta is a constant number they
Yes.
provide, right? Kind of. So now my mu is just 1 over 3 sine theta over cos theta, which is 10 theta, right?
Mm-hmm.
1 over 3 10 theta, which is my mu. Does that make sense?
Mm-hmm. Oh yeah, it does match the answer as well, right?
Oh, okay. Is this one okay?
Yeah. Mm-hmm.
So let's
Maybe.
summarize this. Although it's complicated,
Oh yeah.
but the thing is still sigma torque equals to I alpha. First one, just big one, although analyze, but it's a typical, you will see. And second question is just sigma F equals to MA. See, they have both second law, right? That's why we say Newton is great.
Yes.
It's complicated stuff, it's just Newton's second law. It solves a lot of basically all material motion is involved with this. Does that make sense? So we basically find all the I, find all the sigma torque, and of course you have to do force diagram. You have to do force diagram, and the first one also involves this P and this mg sine theta, and the second one also involves the diagram a lot. Does that make sense? This,
Yeah.
this. Of course, I'm using this one as bad. This is my gravity. This is the component. Does that make sense?
Yes. So long as I remember this, I should be able to be fine.
Yeah,
Okay.
this and also the formula. I mean, not the formula. Also the diagram. The diagram is actually only with the diagram we can analyze it a little bit better.
Oh yeah, because you'll see that F, I mean, was it mg sine is the only torque maker right now. So.
Yes, only the point. Yeah, that's a good. Only torque maker. Yeah. And that's a P. I can write down this sentence. So the P, why we choose this P is we want more force goes through the axis. We want more torque to go through the axis. We don't know. We want more force here. We don't know. We don't know.
Such as friction.
Friction,
here,
we
yeah.
don't know, right? And well, normal force also we don't really know that much by the first question. Only by the second question of analyze we know it's mg cos theta, right?
Yeah,
we
so
want
that's why it's,
Yeah.
this is easier to get than this.
Yeah. So your choice for this center is actually okay. Also get the same answer, but it's just a more complicated. Yeah. For the question one, you need your question two. Actually, I did this before. It's also a good choice. We also, because we always like to choose the center, right? This is what we do normally. We always like to choose this one. And so this
So
principle,
I draw a diagram.
Yeah. So this principle is only for convenience actually, because that one we can have several torque being 0, which is good for calculation. So diagram and second law basically is a summary. I mean, diagram and second law. This is the second law for both angular and cancellation. Does it make sense?
Yes.
We also need that parallel axis theorem, right? Good. 15 is also similar to 15.
Okay. So a cylinder of mass m and radius r rolls without slipping down an incline. Right now. Okay, the inclined, whose inclined angle with the horizontal is theta. Determine the linear speed of the cylinder's center of mass when it reaches the bottom of the incline. Okay.
Maybe it's
So
not that similar, actually. I was wrong. Maybe it was not that similar. Because they mentioned something which is kind of the key. Before they mentioned, now they
they
mentioned
want the
linear speed.
center.
Yeah, they want the linear
Oh,
speed, which
yeah, I
points.
was about to start off with this, but it doesn't work now. That's.
Oh,
But you can go. Sorry.
oh. So it's a linear speed, which is a little key here. So how to do this? The graph is this. The graph is actually given.
I have a feeling we might have to maybe a big 5 as well.
Yeah, yeah, definitely big five in the end. If we don't have big five, we can't really have that linear speed thing.
Yeah.
Hmm.
So I think it's missing. I don't know which equation I should use. I kind of want to do the one without acceleration, but we found acceleration last time. It wasn't that like it's possible to get acceleration. So
Yeah,
maybe the initial velocity. No.
we can actually, if we use the formal questions like answer, that'd be good for 15. Yeah, but that's a little difficult to do. Let's summarize that anyway. Like because in formal question, this is almost the phenomenon. It's just like the previous question, right? There's a cylinder rolling down, right?
Yeah.
Which is a typical case in a lot of wars and natural phenomena. So and then which we find the last one is this, right? This is what we find for the last question, right?
Yes.
We can find the linear acceleration. If we find linear acceleration, we can actually use it because it's basically everything is the same, right?
Yeah.
So I can use
and now we also have.
yeah, you can use this one since you mentioned big five, and this one alone just can solve this question. Oh, that's pretty.
Oh
cool.
yeah, I forgot time's not in there at all.
Yeah.
Okay.
Time is
yeah.
not there. If you want to use big five, this is because this one is 0, which is make my life easier. So v squared is just 0 plus 2 times g 2g sine theta over 3 time my delta x from here to here, which is because they mentioned this one is known as h, and this one is theta. So this the distance or displacement they make is actually h over sine theta. Is that making sense to you? Your delta x.
The distance traveled is h over sine theta. Why is that again?
Because h over delta x is my sine theta. See, this is delta x, right? This is delta x, right?
Oh yeah, inverse.
This is delta. Yeah. So that's why delta x equals to h over sine theta. So I can introduce that one in here. Does it make sense?
Okay.
Yeah.
Yeah.
And so great thing, sine theta can be simplified. So 4gh over 3, I can just square root that, which is my answer. Does that make sense?
Okay, yeah. That's
yeah.
You make it seem not that bad.
Yeah. So this is the previous question's benefits. We find that it's the same phenomenon, and we use that acceleration. That because the acceleration we use a lot of time to prove and analyze and do is 2g sine theta. And this is the reason this 2g sine theta over 3 is the reason we can play like this. Does that make sense? For example, if I have a tree rolling down, you can imagine that happens in the old time war, right? You're using this is only because your acceleration is manageable. You know when you can hit your enemy. Does that make sense? Or when there's an earthquake, with this kind of thing, how they, how long they get there. Does that make sense?
Yeah, because you need that for the big five as well as what is an mg sine theta minus f equals ma?
Yeah.
So
So I'm using all that to find it. But there is a, normally when we do this, because 14 and 15 is not together all the time. So what we want to do is not using A equals, and also it's not required to memorize this. Who can remember this? So if we do it directly, what do you want to do? If we do not use the previous question. We normally want, it's a linear, right? We know it's a final velocity, right?
yeah.
We want to use conservation for this because energy is conserved, right?
Oh yeah,
energy
so
is
you do
conserved.
like something like
I can use mgh.
mgh.
Yes, equals to the final energy is, I don't have potential energy anymore. I have two kinetic energy. One is rotational and one is angular, right?
Yeah, something like that. Final H, yeah.
Yeah. So this one mgh just can be equals with my k1 plus k2. Does that make sense?
Shouldn't it be like mgh plus k1 equals to k2? Because
Sure.
because the mgh gets converted, yeah.
Yeah, so you can say mgh plus a 0 or 0 until your potential energy is getting 0 plus k1 and k2. Is
Okay,
that what you
yeah.
meant?
Not I was doing it like this, right?
Oh, because wait. Oh no, my k1 is not exactly the. Oh yeah, right. What I think what you meant is k initial. If you want to write that, that's k initial and that's k final, right? But my k initial is 0, right? When you start to rotate, it's 0, right?
Does it say that?
Rows down. It's okay here. Assuming it started from rest at the top.
Oh, whoops. Yeah.
And also when they say roll down an inclined plane, normally we're saying that. If they say there's an initial velocity, they will tell you. If they didn't say normally there's not. So mgh plus your initial, which is 0, and v final is the k final is actually when you rotate in ending here, without ending you go on, right? So you have two kinds of, one is since you use that thing, translational, and one is angular. There have two kinds of kinetic energy, right? In the end, one is rotating, direction like this, going in that direction. Also, one is rotate, rotate by the center, right?
Yeah.
So two kinds of. So that's why I'm writing this one. I'm just skipping all the one getting 0.
Oh, okay. Okay, that makes sense because it's total kinetic energy equals this.
Yeah.
Okay, yes.
Yeah,
and
right,
assuming it starts from rest.
Yes.
Okay, yeah, that does make sense.
Yeah, now the problem is just how do I express my kinetic energy? So first, let's say translational. Translational is easy. It's 1 over 2 mv squared.
Yeah.
Also, this one is the one that we want, right? Good. And plus the rotational kinetic energy is what? Remember?
Rotational kinetic energy is
coming from
just kinetic energy times r.
It's because before it's this, right? But we keep that m is inertia, v is my omega, so this is my kinetic energy for rotation. Remember?
Oh yeah, because V just gets converted into that.
Yeah, V is omega. Mass inertia is I, right?
Uh-huh.
So now is 1 over 2 mv squared plus 1 over 2 I omega squared, right? What I mean?
Yes.
Since V is
Mhm.
something we already know, or we really want, V is the unknown, so we might want to keep V in here. So hopefully I can find I. I this time is the one, is the cylinder only, right? Nothing else. Cylinder rotate by itself, which is, let me think about that. Is the cylinder is 1 over 2 mr squared, right? It's the cylinder one, right? The one that you asked me, is it better to memorize? Yes, it's better to memorize it. And then omega squared. Since omega is not what they asked, so I want to use V to express omega, which V equals omega R. Is that, remember this?
Yeah.
Yeah. If that's V, so my omega is V over R. So that's V over R squared. Is that okay? Oh, with this equation, I think we can find V. Because V is the only one that
Yeah.
we don't know.
So we just take everything else in, such as
simplify all the M, and simply this R square and R square also goes out.
yeah.
Hmm.
Or you
There
could
you-
like try to get it out and then get that right, and
Yeah, it's basically, this is 1 over 2 times 1 over 2. It actually now is this mgh equals to saying 1 over 2 plus 1 over 4, right? It's basically 3 over 4 m v squared.
okay, yeah.
And m simplified, so now it's v squared equals to 4 over 3 gh, and then I can find v, right? Same thing as we use the other one to do it.
Okay, yeah, that makes sense.
Yep.
Well, I think we could call it here, and I'll try to redo all those problems.
Yeah, 14 and
Just to
15.
get a
Difficult.
Mhm.
Also,
and maybe
if
the
you,
problems that lead to them, which
Yeah.
is
in the
11
drill.
and 10.
Yeah. And also, you can, when you get problem, you can roll back with, for example, parallel axis theorem, and also well, this kind of thing, right?
Yeah.
Okay. I
Well, I think that could be.
Yeah.
Yeah. See ya. Thank you.
Thank you. Bye-bye too. Bye.